Hello, this is Yuanzhong from University of Texas at Austin, and I'm glad to present our work application-defined decentralized access control. So there are two properties we want about a good access control mechanism. One is simplicity, which means easy to understand and less prone to bugs. And the other is flexibility, which means it is expressive enough to support many use cases. However, the two properties don't coexist well in many practical systems. Operating systems like Unix and Linux choose simplicity over flexibility. They are based on simple concepts like users and groups, and there's a centralized administrator called the root user. However, this model is too rigid, and people have found the need for more flexibility. Therefore, things like setuid binaries are included into this mechanism. And they do make the mechanism more flexible. But on the other hand, they also make things tricky. For example, Apache server has a feature called SUExec, which uses setuid binaries to run CGI or SSI programs with different UIDs. However, the documentation also warns the user that if you aren't familiar with managing setuid binaries, then we highly recommend that you not consider using SUExec. And in fact, server applications typically use their own handcrafted program logic to enforce access control. And although they're running on top of an operating system which already has an access control mechanism, however, access control is hard to get right. And access control bugs in servers are considered as a top 10 security risk. So why can't the operating system help to enforce access control for the server applications? The reason is OS-level mechanism is too inflexible. For example, it typically uses numerical identifiers in the flat namespace for principals. In Linux, both UIDs and GIDs are 32-bit integers. And consequently, if the servers were to use UIDs to represent their own users, then they cannot manage their own principals separately. And it would require mapping between server users and OS UIDs. Moreover, OS tends to have centralized the management of all principals. For example, in Linux, the root or administrator privilege is required to manage users and groups. And principals are typically defined in a few centralized files, like the password file and group file. Therefore, a regular user does not have any power to define an ad hoc group, like a circle in Google+. And creating a server user would require modifying system-wide sensitive files, which is not desired. Although inflexible, OS mechanism tends to be more robust than application mechanism. Therefore, it's being used for several applications for several use cases for better application security. For example, SSHD is a privilege-separated program which runs different components under different UIDs. And in Android, each application is given a unique UID to isolate it from other apps. And in Mac OS X, there's an application sandbox called Seatbelt. We refer to the scenarios we talked about so far as user or application-defined access control. They are all related problems, but in practice, they are usually solved in very different ways. So the question is it possible to find a unified OS-level approach which support all these scenarios with a balance between simplicity and flexibility? We present DCAC, which stands for Decentralized Access Control. It is conceptually similar to the traditional UNIX discretionary access control, or simply DAC, but it's also made more flexible and generalized to support the scenarios we talked about before. It uses a unified model which is familiar and intuitive to both users and developers. For example, it can still naturally support concepts like users and groups. And finally, coexist with DAC. Here's a summary of mechanisms used in DCAC. DCAC has a basic attribute-based model and also mechanisms for coexisting with DAC. For each of them, we have mechanisms for both augmenting and restricting privilege of a process. We'll introduce each mechanism next. DCAC is based on attributes. It uses attributes to identify principals. Instead of using a flat namespace, attributes are hierarchically named strings with components separated by dots. A child attribute is generated by appending a suffix component to its parent. For example, .u.alice is a parent attribute of .u.alice.photo, and we say a parent attribute represents a superset of privilege of Alice child attribute. Attribute is a generic abstraction. It can represent different types of principals, including OS user groups, server user groups, individual applications, and even application components. So, but we still have some naming convention for traditional concepts like OS users and groups. We use .u.username and .g.groupname to represent them respectively. Next, we'll talk about what credentials a process or a file may have in DCAC. In Linux, a process carries credentials like a UID and a list of GIDs. And similarly, in DCAC, a process carries a list of attributes, which we call the attribute set. Like the UID and GIDs, attributes are inherited across events like fork and exec. In Linux, a file has permission base, a UID, and a list of and one GID, to specify the permission on it. And similarly, in DCAC, a file has an ACL in terms of attributes. The ACL has 4 access modes: read, write, execute, and modify. Each of them is a formula of attributes in disjunctive normal form without negations. So we explain the 4 access modes with a comparison to the traditional DAC. The first 3, read, write, and execute, are functionally identical to the RWX permission base in DAC because they both specify the permission to read, write, or execute the file. And the modify access mode is similar to the UID in DAC because they specify the admin privilege over this object. In DAC, if the process has the same UID as the file, then it can change the permission based on this file via chmod. While in DCAC, if the process satisfies the modify access mode of this file, then it can modify the ACL of this file. So a key feature of DCAC is that it allows any process to change its attribute set. For example, a process can add a child attribute of any existing attribute in its current attribute set, and the process can always drop any attribute. Adding a child and dropping a parent can be used as a way to deprivilege a process, and it doesn't require the process to be root. In this sense, DCAC is decentralized in privilege, compared to Linux, where the setuid syscall is only restricted to root. Here's an example about creating a sandbox for a PDF viewer. Suppose user Alice has a shell process which carries .u.alice. Then it can fork a child process which adds a child attribute .u.alice.pdf and drops the parent. Now it can invoke the PDF viewer, which will be sandboxed in a way such that it can only read files which has .u.alice.pdf in their read access modes. We can also use attributes to represent server users. Suppose the server has a dispatcher process which has .apps.server, and it receives 2 requests from different users, Alice and Bob. And for each of them, it forks a child worker process, and each worker process will add a child attribute representing the user. Now they drop the shared parent attribute. When they process requests for different users, access control decision will be made by operating system. And so far, we only talk about how a process can deprivilege itself, but sometimes we need to augment the process privilege. In Linux, there are setuid binaries, like the pseudo binary, which allows the process, which allows the user process to become root if the user is in group admin. And in DCAC, we have a mechanism called attribute gateways. For example, we can represent an ad hoc group using a gateway. The gateway will allow a group member's process to add this group attribute, which is a way to augment the process privilege. Ad hoc groups are created and managed by regular users instead of the system administrator. So an ad hoc group needs to specify both the regular members and admins of this group. For example, here, the group is called reading group defined by user Alice, which has 2 members and 2 admins. Then we'll explain what a gateway is and how it can represent an ad hoc group. The gateway is just a special file in the system. And first, we'll choose an attribute .u.alice.reading group to represent this group. It is a child attribute of .u.alice, which means it's under control of user Alice. Then you can view the gateway as an ACL of this attribute, which has 2 access modes, read and modify. The read access mode can be used to specify the regular members of this group, while the modify access mode can specify the admins of this group, which allows the process to have admin privilege over this attribute, which means the process can modify this gateway or create new gateways for the same attribute. Ad hoc groups can also be used in a server application. For example, here, server user Bob can define a group called friends, which includes Alice within a gateway. And according to this gateway, Alice will be processed as the group attribute. And DCAC as a generic kernel level mechanism doesn't enforce the location of gateways. But likely, specific OS distributions or applications may develop their own conventions. As a result, different applications can manage their own gateways separately without interference with each other. And they don't need to synchronize on a global policy file. A design goal of DCAC is to coexist with the traditional discretionary access control, or DAC. So instead of replacing the UID and GIDs, we still keep them in a DCAC process. And we decide to grant access when either DCAC or DAC allows it. This means a valid Linux disk image is still a valid DCAC disk image, which enables incremental deployment. However, this also means the system becomes more permissive than DAC only. So we need a way to restrict DAC in many cases because we want to isolate processes with the same UID but different attributes. Therefore, we introduce two new pieces of state in the DCAC process, pmask and UID bit. The pmask is used to restrict the permission bits on files. So before the permission bits are passed to a DAC check, they will be first ended with the pmask. Therefore, if the pmask is 555, it means DAC cannot grant any write permission. And for UID bit, if it's 0, it means the process gives up the UID-based ambient authority in DAC, which means, for example, DAC cannot allow the process to chmod. And importantly, a process can only clear the bits in pmask and the UID bit to deprivilege itself, not the other way around. You may wonder how we can bootstrap DCAC, because attributes can only be added based on the current attribute set. So who sets have the very initial attribute. To solve this problem, we still keep the concept of root and we allow a root process to add any attribute, although we do avoid the use of root in many cases. Then we modify system binaries like login SSHD and like DM to set up the attribute set of a user process when the user logs in. We add .u.username with admin privilege and .g.groupname without admin privilege to this process. As an implementation detail, we store ACLs of persistent files in extended attributes. But we still keep an in-memory cache for every ACL to support in-memory files, IPC objects, and to improve performance. But the ACL can be invalidated by certain file systems, including NFS, according to timestamps or hashes. To show how DCAC as a single model can support different scenarios, we built several applications. First, we have a wrapper program which sets up a sandbox for unmodified applications. The unmodified application will be sandbox because DCAC state is inherited over fork and DCAC. Then we modify server application DokuWiki to use DCAC to enforce its access control and to also support ad hoc groups. We also modify NFS to allow DCAC to operate on multiple machines. And DCAC has natural support for NFS because it doesn't require a global attribute server. And finally, we modified SSHD such that it allows a regular OS user to define his or her sub-user, and sub-user can log into the system with a subset of OS user privilege. We evaluated the performance of DCAC with file system microbenchmarks on small files. We choose small files because DCAC only adds overhead on operations like open, create, and delete. The result is for local ext4 file system, if the ACL is small enough to be contained inside the inode, then the slowdown is under 4%. But if the ACL is large to require extra disk blocks, then the slowdown can be up to 9%. However, for NFS, the slowdown is always below 5%, and ACL size has a small impact. Because the performance is dominated by extra round trips for fetching ACLs, which fortunately are not common because ACLs are cached in memory for most of the time. We also have several macro benchmarks. For kernel compile workload, we observed under 2% slowdown for both ext4 and NFS. And for DokuWiki, we didn't observe any slowdown when we played back over 6,000 revisions to our website. And to conclude, DCAC generalizes OS access control to support more user or application-defined scenarios. And DCAC avoids the need of root privilege in many use cases. And it doesn't require centralized management of attributes. And finally, DCAC coexists with discretionary access control. Our code is available on GitHub, and thanks.
This is Yanlin Li from CMU. This is very nice work. Congrats. And I have a question on the access control policy. Is that possible for one application to define different access rights for part of the applications? For example, a part of application can have higher access right or different access rights.
Yeah, sure. So for example, in a server application, you can have, for a dispatcher process, you have the parent attribute, but for each worker process, you only have attributes representing the user. And also, you can imagine you have browser, and each tab has a child attribute of the master process.
Peter Desnoyers, Northeastern. My first reaction to this is, this seems too easy. So what were we missing before?
I think I've
thoughts on that. Yeah.
I think I've covered most of the important things in this talk. And as we said, we think this is a simple model which is easier to understand. And you think it's too easy, but it's also a nice thing to have, right?